So in this next lesson, we're going to look at the Halogenoalkanes. Halogenoalkanes. And we looked at these at the end of the last lecture as the product of the reaction between halogen, in that case chlorine, and an alkane. And this was a free radical mechanism, so it needed either heat or light, and that resulted in a halogenoalkane. And as a byproduct, you would also get HAl. So that was, for example, HCl. And so now we're going to take these halogenoalkanes and we're going to explore their reactivity. So these are important chemicals. You might recognize one of the most famous classes of halogenoalkanes, which are chlorofluorocarbons, or CFCs. And the chlorofluorocarbons we're responsible for the degradation of the ozone layer. And we'll talk about the chemistry of that in the third lecture in the halogenoalkanes set. But chlorofluorocarbons is one form of halogenoalkane. They've got chlorines and fluorines on them, but there are all sorts of other uses for these as well. And so we don't want to restrict ourselves just to the ones with the bad rap, as it were. So we're going to talk about the nucleophilic substitution reactions of halogenoalkanes with 3 different nucleophiles. Now, need a little bit of background here. A nucleophile is so-called nucleo, meaning the center of the atom, so the positive part, and phile, meaning to love. So a nucleophile is something that loves the positive part. So it's basically attracted to positive things, okay? So if I draw a nucleophile over here, this likes to go towards positive things. Now, you probably know that that means that a nucleophile is going to be kind of a bit negative. And I don't mean it's a bit of a downer, I mean it tends to have more electrons than you would expect perhaps, or it's got a high density of electrons. Because electrons are negative, those are what's attracted to the positive site. So nucleophiles love the positive part, they're attracted to positive sites. Electrophiles these love the electrons, so phile again love, and electro is negative. So these love the negative. So if I draw E as an electrophile, and I show it likes to head towards negative things, then that means that we know that the electrophile must be kind of a bit positive. Now be careful, this doesn't necessarily mean that they are charged. So some things are charged. For example, earlier on we talked about sodium hydroxide, okay, and we drew that as OH minus. So this is charged, but not all nucleophiles are charged. So for example, we're going to talk about NH3, which is ammonia. That's got no charge on it, it's neutral. But what it does have is a lone pair of electrons. Electrons are negative, so this lone pair of electrons acts as an electron source for it to be a nucleophile. So these can then go and do nucleophile things by heading for positive centers. So don't get confused. Don't think of nucleophiles as necessarily being negative. Don't think of electrophiles as necessarily being positive. They sometimes are, but also they might just be areas of high or low electron density. So an electrophile might have a particularly low area of electron density, and a nucleophile might have a particularly high area of electron density. And that would be enough to get them to react together. Now again, because we are doing organic chemistry and that talks about the flow of electrons, we tend to draw our curly arrows going from the nucleophile to the electrophile, because that demonstrates the electron flow from the negative thing to the positive thing. So now that we know a little bit about nucleophiles and electrophiles, let's move on and let's talk about some nucleophilic substitution reactions with the halogenoalkanes. Now that sounds maybe confusing, but let's break it down. So nucleophilic just means nucleophile, Substitution. Substitution just means we're going to swap one group with a different group, and of Halogenoalkanes. We've already looked at these, so you know what they are. So if, for example, we had chloromethane, and we were going to react that with a nucleophile. Now there are three nucleophiles that you need to be able to draw mechanisms of. They are hydroxide, for example, like we did earlier from sodium hydroxide. They are cyanide. Yep, it's the dangerous stuff. So that comes from sodium cyanide or hydrogen cyanide. And then the last one, which I mentioned briefly earlier, is ammonia, NH3. And that's the tricky one because it doesn't have the charge. So here we have three nucleophiles. And you need to be able to draw the reaction mechanism of each of these with any halogenoalkane. Now, I've picked chloromethane, but the chlorine could be bromine or fluorine or iodine, and there could be more carbons in this chain. So, for example, if I just pick a different colour here, I could have carbon-carbon, and this would then be chloropropane. Okay, so let's stick with chloromethane for now because it makes the mechanisms easier. And I'm going to do this using the full displayed formula, and then I'm going to do it again using the skeletal formula. So let's start off with the displayed formula, and I'll redraw this out here. So I'm going to put my chlorine on the other side because it makes life a little bit easier. So I've got my carbon, it's got 3 hydrogens, and it's got a chlorine here, and this is chloromethane. Chloromethane. I'm going to pick the first of my 3 nucleophiles, so I'm going to pick this guy, hydroxide, and my hydroxide is here. Hydroxide. And I'm going to draw it with its negative charge, and I'm going to also draw a lone pair of electrons on here. Now comes the good bit because we get to draw our curly arrows, which is always very satisfying. Remember, the curly arrow starts from the lone pair because it's a flow of electrons. It ends where the electrons go, so in this case the electrons attack the middle carbon atom, and then they go on this bond, the electrons leave and they go away with the chlorine. Now I've just shown you there what happens, but you might be thinking, well, why does that happen? That's a good question, so let's have a look at that. Let's look more carefully at the chloromethane molecule. So here's my chlorine and my carbon and my 3 hydrogens. Now you've probably come across the concept of electronegativity. And this means how much things like electrons. Okay, so how much things like electrons. So if something's very electronegative, that means it really likes its electrons, and if something's not very electronegative, it means it doesn't really care about its electrons, it's happy to let them go. Now, if you think of the periodic table, which I'll just do a quick sketch of here, so it looks something like this, doesn't it? Electronegativity increases from the bottom left to the top right. What this means in practice is that chlorine is more electronegative than carbon, so there is a little bit of a negative charge on the chlorine and a little bit of a positive charge on the carbon. This symbol that I've used here, that I'm just underlining in green now, this is just a lowercase delta, which is a Greek symbol, and all it means is a little bit. So here I've got a little bit of minus and a little bit of plus. It's not enough that it's a full-on charge, so I can't, for example, draw negative here and positive here. The electrons are still in the covalent bond in the middle here that's yellow now. They're still in that bond, but they're slightly more towards the chlorine than they are towards the carbon. So what that means in practice is that I've now got a slightly positive centre on my carbon. And if you remember, things that have a slightly positive centre are electrophiles. So here I've got an electrophile, for example, and electrophiles like nucleophiles. So now let's look at the hydroxide. So I've got my hydroxide here. Oops. Hydroxide here. And this has got a lone pair of electrons and a negative charge. And this means that this is very negative. It doesn't even have to be a little bit negative, it's just negative. We've got that charge there. So I've now got a negative thing, so that's a nucleophile, so we put nucleophile, and I've got a positive, slightly positive thing up here, so that's my electrophile. And that means that when I draw my curly arrow, I know exactly where it's going from, and I know exactly where it's going to. Because I start at my nucleophile, always start with the nucleophile, and I go to the electrophile. So the negative hydroxide is attracted to the slightly positive carbon, and that carbon's slightly positive because the chlorine is there. The electrons in this carbon-chlorine bond, and this carbon-chlorine bond, are now happy to leave because they're being pushed out by the electrons coming in from the hydroxide. So they leave out here, and they're being pulled towards the chlorine anyway. So the chlorine is pulling electrons out of the carbon-chlorine bond, just as the hydroxide pushes electrons in from the other side. And that makes this carbon-chlorine bond easy to break because the electrons are being pushed and pulled at the same time. So they are very happy to take off and go away with the chlorine. So if I then finish off my reaction on the left, you then end up with COH, H plus Cl minus. So this is the displayed formula reaction for the nucleophilic substitution of chloromethane with hydroxide. And what we're left with is methanol, and you should be able to name that by now, and chloride. Chloride ion. So that's the mechanism for hydroxide, but actually I could replace that hydroxide, this hydroxide with anything else, any other nucleophile. So I could draw that as being Nu. I'm going to draw it with a lone pair, and I could pull my arrow around so that it's like that. And that's now the general equation. If I change this as well, make that Nu for nucleophile. Now we can do the same thing and just swap out different nucleophiles. So I'll show you the same thing, but I'll show it using skeletal formula, and I'll show it you using a different nucleophile and a different electrophile. So instead of chloromethane, we're going to go with one that we talked about earlier, which is bromopropane, 2-bromopropane. And we're going to react that with one of the other nucleophiles that you need to be aware of using, which is cyanide. But it's the same process. So I get out my curly arrow tool, and I start from my lone pair, and I go for the carbon center that is slightly positive. So I'm just going to draw that on there briefly. So I've got a slightly positive center there and a slightly negative bromine. So after my electrons come in, get rid of those. After my electrons come in, they then push out the bromine, kick out the bromine, and then the result is then this is 2-cyanopropane and a bromide ion. So exactly the same mechanism. I've just swapped the electrophile and the nucleophile for different ones, and I've used the skeletal formula instead. So just to explain that fully, I'm going to draw in now the carbons that I would expect to have on here. So there's one carbon here, carbon here, carbon here, and those 3 carbons are here on the left right hand side. And then I'm going to draw in the hydrogens in yellow just to complete this. So there's 3 hydrogens there. Hopefully you can see now why I like using skeletal formula, because it's much simpler and doesn't mess things up as much like this is. This carbon needs another hydrogen, and same thing on this side. So hydrogens all the way around here, hydrogen here, hydrogen here, hydrogen here. So that's what it looks like if I was to draw it out fully, but because I don't like doing that, I've just used this little formula. So I'm now going to just delete all of the things I've just done, and hopefully it's simple and you can understand it and you can see what's going on. So I've got two bromopropane, I've reacted it with cyanide, and I've got two cyanopropane and bromide. And you can repeat this with any nucleophile that you're given and any electrophile, and it's the same mechanism. You just need to make sure that your nucleophile heads for the positive center on the atom, on the molecule. So that's nucleophilic substitution, and you might be saying that's all very well, but which would be quicker? Would it be a faster reaction if I was to react cyanide, for example, with bromopropane plus cyanide versus chloropropane with cyanide? So this is a good question. So which is faster? So maybe you just want to pause this for a moment and have a think about that and see if you can come up with an answer as to which one's faster, but also, very importantly, why. So if you pause it now and have a think about that. Okay, so two things can affect the speed of this reaction. One is how quickly the cyanide, this guy, and how easily it can come and attack here. And that depends on how positive this center and this center are. Now, bromine is less electronegative than chlorine is, so it draws the electrons away much less. So therefore, on bromine, this center is less positive. I'll say all of that again. Bromine is less electronegative than chlorine. That means that bromine pulls electrons less strongly than chlorine, and that means that for bromopropane, the electrons are less pulled away from the carbon, and therefore that carbon positive is less positive. It's a little bit positive still, I can still draw it as delta positive, and this bromine is still delta negative, but it's really little. Whereas on the chlorine, it's nice and big. So you get a big positive center. So the nucleophile prefers to attack a more positive center. So with that information, you might say, well, in that case, I'd expect the second reaction to be faster because the cyanide can find that positive center more easily. And that's all very well, but there's actually a second step. And the second step is the breaking of the bond between the carbon and the halogen, whether that's between the carbon and the bromine or the carbon and the chlorine. And that step is actually what dominates these reaction kinetics. So the speed at which this happens, the speed at which the bond between the carbon and the chlorine and the carbon and the bromine breaks, is critical in determining the speed of this reaction. And carbon-bromine bonds and carbon-chlorine bonds have what we call a bond enthalpy. And this means the energy which is stored in the bond. And that determines how easily that bond is broken. So carbon-bromine bonds break much more easily than carbon-chlorine bonds. And that means that the carbon-bromine reaction is much quicker than the carbon-chlorine bond reaction. So halogen bromides, bromoalkanes are more reactive than chloroalkanes. And that trend continues for the whole group. So if I have fluorine, chlorine, bromine, iodine, I have reactivity increasing down the group. Reactivity increasing. And this is because of a change in bond enthalpy as you go down the group. So that's everything you need to know for AQA AS level chemistry on nucleophilic substitution of halogenalkanes. In the next session we're going to talk about elimination reactions where the halogen is lost from the molecule and gives you an alkene. So we'll cover that in the next session.